By now, it feels almost pointless to say it out loud, but drones have quietly rewritten modern warfare. Despite how often this has been stated, for many militaries, the widespread use of drones remains uncharted territory. Instead of looking at and once again talking about the current losers of this race, we would like to examine the frontrunners. Specifically, the country that in many drone categories has both qualitatively and quantitatively surpassed everyone and only has one real adversary in that technological competition. That country is Russia. Today, our intention is to give a detailed overview of Russian unmanned aerial vehicles, most of which were employed in Ukraine. It is also important to note that we will not cover the ubiquitous small quadcopter FPVs, or first-person view drones, in this overview. Those off-the-shelf or improvised solutions, often assembled like Lego kits, number in the dozens of types and deserve a separate analysis entirely. Instead, we will focus on well-defined, standardized factory designs, drones that have more fixed configurations and roles. Now and then, we will also dive deeper into specific examples of how particular drones were used during the war. This, unlike any list of models that can always be extended by new types in the future, will remain a relevant reminder of the irreplaceable role of drones on the current battlefield. We start our overview of Russian drones with ISR models, those used for intelligence, surveillance, and reconnaissance. A staple Russian ISR drone, developed long before 2022, is the Orlan 10. By 2022, over 2,500 Orlan 10s had been produced, spanning 11 different variants. Early model Orlans had an almost embarrassing internal design, a commercial Canon DSLR camera secured with a Velcro strip. The fuel tank for its small gasoline engine was a plastic bottle, complete with a screw-on cap. In appearance, with its downscaled World War II fighter-like fuselage and tiny piston engine, the Orlan 10 did not look particularly intimidating. And due to the use of a basic still camera, early models couldn't even send real-time video. Modern Orlan 10s, however, share little with those pre-war models. The trademark plastic bottle fuel tank remains, but the optics have been upgraded and are no longer rigidly mounted. Current Orlans can broadcast live video to operators. This improvement, achieved while keeping the airframe simple for mass production, has allowed the Orlan 10 to evolve from a simple spotter for missed-ass howitzers into a real-time reconnaissance workhorse for any target of interest. There have even been reports that some Orlans were adapted to drop small munitions like OFSP bomblets, as well as serve as carriers of FPV drones in addition to their reconnaissance role. Also, prior to 2022, a bigger version, the Orlan 30, was developed. It features a 7-liter fuel tank versus the roughly 4 liters in the Orlan 10, yes, still a plastic bottle, and a 2-cylinder engine instead of a single cylinder, allowing greater endurance. More importantly, its ISR package is much more advanced. A gyro-stabilized turret with multiple sensors that not only provides optical zoom but also includes infrared and low-light night vision cameras, a rangefinder, and even a laser target designator to guide precision munitions. This represents a significant jump in technology from the crude original Orlan 10, a theme we will repeatedly see in this overview. Often quite questionable solutions that the Russians initially brought into combat were eventually refined, and, in the process, surpassed many alternatives used by, for example, NATO countries. The Orlan series is far from the only ISR drones that Russia fields. Other fixed-wing recon UAVs with small piston engines, such as the Phoenix, the Merlin VR, and the Patero G0, have been deployed as well. These have similar conventional layouts resembling small airplane-like drones and capabilities, complementing the Orlans. They are produced in somewhat smaller quantities, yet likely still in greater numbers than the entire drone fleets of most European countries, underscoring how heavily Russia has invested in this category. Some models, like the Granat 3 and 4, have slightly different configurations, for example, engine placement, while carrying similar to Orlan 30 cameras and laser target designators. Those tweaks affect the price and heat signature, but they all perform a similar role of day-to-day aerial reconnaissance for field commanders. Where clear advantages do emerge is in the vertical takeoff and landing, or VTOL, recon UAVs, such as the AX V300 and the Dragon F300. Most of the aforementioned drones rely on launch rails or catapult devices to get airborne, and then deploy parachutes to land. The parachute recoveries are meant to safely bring the drone down when a mission is complete, but in reality, they can still result in damage upon impact with the ground. Moreover, using a catapult launcher exposes the operators and takes time to set up. By contrast, VTOL drones, typically multi-copter or hybrid designs, take off and land on the spot like a helicopter, eliminating those issues. However, nearly all of those are electric-powered, not gasoline or diesel. This introduces another challenge. Recharging batteries is a much lengthier and more equipment-intensive process in the field than pouring fuel from a jerry can. VTOL drones also have, on average, only around 4 hours of flight time compared to the 8 or 16 hours for piston engine analogs, and even other electric drones without such capabilities. So each type has its advantages and disadvantages. Both are used on the front line for reconnaissance, with the choice often depending on specific mission, resources available, and field conditions. Continuing with drones that use electric engines, Russia has a wide range of lightweight ISR models, often with tailless or unusual airframes designed to maximize glide efficiency and extend flight time on limited battery power. In this broad category of electric recon drones are systems like the ZALA 421-8, Z16, Z16-2, SuperCam S180 and S350, SCAT 350M and the SCAT 450M, Albatross M5, Serik 2, Storm, Tachyon, or even the ominously named Knyaz Vieshi Oleg. In addition, there is an entire family of aileron UAVs, Aileron 3, 7, 10, and 16, which all share a similar flying wing design and role, but scale up in size and capability with each version. All these electric drones fill a specific niche within the ISR hierarchy. So, while it's not useful to delve into dry specifications for each, it's worth understanding how the Russian military employs them together in a layered fashion. For example, if you want persistent observation over a wide area, something that can stay aloft for most of the day and continuously feed data to artillery units or headquarters, a piston engine UAV like an Orlan 10 or 30, the Phoenix or Merlin VR, is the obvious choice. In such a case, the Orlan 10 and Phoenix, depending on availability, also will not be the first choice due to weaker optics. At the same time, they all act as a kind of continuous eye in the sky, or an airborne surveillance asset that commanders rely on almost unconsciously. Their endurance, 8 to 16 hours, makes them ideal for monitoring logistics routes, artillery positions, and troop movements over extended periods. On the other hand, if the task is a short-term tactical reconnaissance, especially in a contested or rapidly changing environment, then electric UAVs dominate. Platforms like the ZALA Z16, Z20, SuperCam S180, or smaller ailerons are better suited for battalion or company-level missions, where the priority is fast deployment and quick situational awareness, and where losing the drone is acceptable. These are often hand-launched or rail-launched within minutes to answer very specific questions. Is that tree line occupied? Did the enemy relocate that artillery battery? Is there movement behind that village? Once the question is answered, the drone's mission is complete. Their typical flight times can be less than 4 hours, enough for a short scouting hop over the nearest hill or forest. Larger electric recon drones, such as the SuperCam S350, SCAT 350M, Albatross M5, or SCAT 450M, occupy a middle ground. They don't match piston engine UAVs in endurance, but they offer better optics and longer range than the tiny tactical scouts. These are used when commanders need better image quality or wider coverage than a mini drone can provide, but do not want to risk or wait for a long endurance asset. In this role, they often bridge the gap between frontline units and higher-level ISR assets. Overall, what becomes evident is that Russian UAVs are not meant to compete with one another once deployed on the battlefield. They are meant to layer coverage. Small electric drones answer immediate questions close to the front. Medium electric platforms expand situational awareness a bit further out. Piston engine UAVs, like Orlan, provide persistent surveillance in the operational depth. Together, they form a continuous network of observation nodes, where the loss of any one drone type rarely collapses the system as a whole. This layered approach also explains why many of these designs appear crude, repetitive, or conservative. The priority for Russians is not elegance or cutting-edge technology. It's availability, replaceability, and functional overlap. If one drone type is unavailable at a given moment, another can usually fill the gap. Perhaps less efficiently, but well enough to keep the information flowing. And this emphasis on obtaining information, on seeing first and seeing continuously, is exactly what sets the stage for the next category of drones. Once reconnaissance became reliable and routine, the next logical step is to direct a high-precision strike on the target. This is where loitering munitions or strike recon UAVs enter the picture. We start this category off with perhaps the most famous of all Russian attack drones, The Lancet loitering munition. In fact, there are at least 2 distinct Lancet series seen on the front line. The original light version, sometimes called Lancet 1 or ISDALI 51, and the heavier Lancet 3 or ISDALI 52. For a long time, its warhead in both versions has been, somewhat surprisingly, a KZ-6, which is a Soviet-era engineering demolition charge originally meant for blowing up structures. This fact only became apparent after dozens of Lancet strikes were analyzed, and it explains why Lancets have a rather random effect against armored vehicles. The KZ-6 can penetrate armor, but it was not designed as an optimized modern anti-armor warhead, so results against protected vehicles vary wildly depending on angle, standoff, and hit location. This explains why many hits often cause damage, but not necessarily a kill. In newer Lancets, the warheads vary, as even anti-tank PTM-3 landmines were found inside them. Quite ironically, the Soviet block of TNT might be one of the few, if not the only, non-foreign parts of this Russian drone. The heart of the Lancet, its onboard control module, remains a NVIDIA Jetson TX2 computer, used for target recognition and control, paired with a Z-Lynx Zinc programmable logic chip, both made by American companies. In Lancet wreckage and components recovered in Ukraine, investigators repeatedly find a range of Western-made electronics, indicating Russia has been able to acquire critical parts despite sanctions. And indeed, most other Russian drones also rely on Western or Chinese tech, often imported via third countries simply because Russia's microelectronics industry cannot produce equivalents. Yet, by importing huge quantities of components from China and other countries, and with some reverse engineering or repurposing, Russia has been able to mass-produce quite effective drones, while many countries that actually pioneer and manufacture such components struggle to field equivalents in meaningful numbers for their own militaries. It's important to highlight how Lancets are used in practice. Some versions have an impressive range of up to 120 kilometers, allowing strikes deep behind enemy lines. However, in typical use, they are not lone hunters. They are usually part of a system of systems. A reconnaissance drone, often a small ZALA ISR UAV, works in tandem with the Lancet, often with operators in the same position. The recon drone, with its better optics, first locates and identifies a target, say an artillery piece or a radar, and provides its coordinates. The Lancet, which has a more modest camera and a narrow field of view, is then launched and guided towards the target coordinates blindly for most of the flight. Only when it gets close does the Lancet's own camera pick up the target for terminal guidance. In many documented cases, the initial spotting is done by a larger drone like an Orlan 10 or Supercam S350 orbiting high up. The Orlan feeds coordinates to a crew of a closer ZALA drone with high-res optics, which then confirms the target. Because the ZALA itself may have a limited range, sometimes other UAVs act as a signal repeater to relay commands, so that the strike controller can maintain a data link with the ISR UAV over long distances. At this point, we no longer have a single strike drone, but an integrated hunter-killer drone team that makes Lancets effective far beyond the line of sight. For example, against Ukrainian planes on open airfields or artillery positioned well behind the front line. Without the more advanced optics and overwatch from ISR drones, a Lancet on its own would struggle to find, identify, and accurately hit anything but obvious stationary targets. So despite the hype, it is not a miracle weapon. It has notable limitations such as mediocre optics, suboptimal warhead, limited maneuverability and final approach, and complex controls. But it remains a dangerous asset because its long range and loiter time allow it to hit valuable targets that were previously safe behind the front. Each Lancet costs an estimated $35,000 to $55,000, making it a relatively cheap way to destroy or damage a piece of equipment worth many times more. In a similar manner, Russians have also used the smaller Cub-type loitering munition in tandem with an ISR drone. For example, there were instances of Cub-2 attack drones being guided by a Granat 4 UAV. This also highlights the rapid modernization pattern. The Cub-1, introduced around 2019, has no camera at all. It was an early kamikaze drone that proved not very successful. Then the design was improved in Cub-2 by adding a camera and even rudimentary computer vision algorithms to assist in targeting. In effect, the Cub-1 was also the father of the Lancet, and the Lancet's success fed back into an improved Cub-2. Overall, the Lancet has become one of the most successful Russian attack UAVs on the front line. largely because other competitors in the same niche, such as the V2U, Scalpel, Rus PE, Isdalai 53, and Chernica 1 and 2, all have more limited ranges, usually under 40 to 60 kilometers, while carrying similar-sized warheads. Next, we should mention a class of attack drones, built with an even greater focus on low cost. After all, a Lancet is effective, but still not cheap enough if you intend to saturate a battlefield. The drone complexity also allowed production and immediate use of an average of 100 to 150 Lancets per month, with the peak in May of 2024, with over 300 used. So, to truly flood the front line with expendable one-way drones, the Russians developed crude designs like Privyet 82 and Molniya 1 and Molniya 2. If the Molniya 2 looks at least somewhat serious, carrying around 10-kilogram payloads up to 60 kilometers and using 2 piston engines on wings, the other two are basically held together by determination and duct tape, rather than advanced materials. Made out of plywood, chipboard, cardboard elements, and copious duct tape, these have a range of less than 30 kilometers for a 5-kilogram payload and short flight time, due to the small battery that powers the tiny electric engine, as well as poor accuracy and often no camera at all. On the flip side, they reportedly cost only around $500 or less in materials, which means volunteer groups or small factories can churn them out without advanced machinery or components. The simplicity also offers high customization, as all 3 drones above were seen carrying RPG anti-tank munitions, landmines, KZ-6, FPV drones, or even just supplies to infiltrated groups of infantry. Their extremely low price might seem to outweigh any shortcomings, but in practice, these devices have proven almost comically unreliable, and dangerous even to their own users. They frequently malfunction and rarely hit intended targets unless used at very short range against large, fixed objects. In essence, they are unguided rockets with wings. Still, Russia has shown a willingness to experiment with these stick-and-tape drones, possibly hoping to launch them in large salvos, or further expanding logistics. It's a quantity over quality approach taken to the extreme, and as of now, simpler and customizable drones are slowly pushing Lancets out of the market due to cost. With that, we have covered the bulk of Russia's short to mid-range attack drones that operate around the front line and can penetrate a few dozen kilometers behind it to hit targets spotted by reconnaissance. For any adversary, these loitering munitions create significant problems, because the Russians can field many types in large quantities in attempts to take out logistics nodes or high-value assets, artillery, radar, air defense units, parked aircraft, etc., behind the lines. Almost all the drones we've mentioned in this category are launched via lightweight portable catapults, often literally a metal rail with bungee cords that can be set up on the ground or mounted on a truck bed. It's worth remembering, though, that these strike drones are just one fragment of a system, relying on the constant frontline surveillance provided by the piston engine UAVs and the mission-specific electric UAVs we discussed earlier to actually find targets and guide the strikes. After suffering significant losses to Lancets and other strike drones in 2022 through 2023, the Ukrainians tried many ways to counter them. The most recent approach, using interceptor drones, looks like a step in the right direction. Initially, makeshift anti-drone FPVs, basically ordinary FPV quadcopters modified to ram airborne targets, were tried. Later, Ukraine began developing dedicated interceptor UAVs with higher speed and better endurance to chase down enemy drones. A famous example is the Ukrainian Sting drone, a small, fast quadcopter designed to hunt Lancets, Shaheds, and ISR assets. The Russians, however, were quick to copy this idea and have already at least prototyped their own UAVs of this class, such as Sukhoi, Yolka, Skvorets, PVO, Bolt, Kinzhal, Kresnik M, and others. In addition, the extra cameras on ISR drones were placed to start maneuvering upon interceptor approach, and this measure-countermeasure dance continues. It is notable that the key reason Ukraine invested heavily in anti-drone FPVs and then specialized interceptors in the first place was the daily Russian deep strike drone attacks on Ukrainian cities, which we will discuss next. Moving to the heavier drones reserved for long-range strategic strikes, the king of this class is undeniably the Shahed 136 and its Russian derivative Geran 2. The story of this UAV is best described as a never-ending and impressive cycle of adaptation by both sides. Russia's aim in using these was to maintain constant pressure on Ukraine's critical infrastructure, primarily the electrical grid, power plants, heating systems, and the defense industry. Ukraine's aim was to constantly improve countermeasures to shoot down most of the drones before they could reach their targets. Let's chronologically walk through this cat-and-mouse game as it offers a meaningful insight into design evolution. We'll start with the Shahed 131, a smaller alternative to the well-known Shahed 136. The first batch of Iranian-made Shahed 131s, named Geran 1 in Russia, was used in October 2022 when they attacked targets deep behind the front line, reaching key Ukrainian cities. It quickly became apparent that while referred to as drones or UAVs, they function more like slow, noisy cruise missiles. They have a piston engine that emits a distinctive loud moped noise, a delta wing layout, and they use satellite navigation, civilian GPS, or GLONASS for mid-course guidance on a pre-programmed path. They launched from simple rail launchers, sometimes even put on trucks and using a solid booster, after which the little gasoline engine takes over. Russians also quickly complemented the smaller Shahed 131 with Shahed 136 or Geran 2, because those carried way heavier warheads, roughly 15 to 50 kilograms. At the same time, those were quite expensive, around $250,000. So, Russians started establishing domestic production with support from their Iranian allies to cut the costs. Naturally, once these drones started raining down in swarms on Ukrainian cities, the search for effective defenses began. At first, Ukraine threw whatever conventional air defenses were available at the problem. Fighter jets were scrambled, surface-to-air missiles from systems like S-300, Buk, even NASAMS and others were used to shoot down drones. While this worked to an extent, it was hugely inefficient. Each SAM could cost anywhere from $100,000 to $1 million, versus perhaps $20,000 to $70,000 for a Shahed drone after the full domestic cycle of production was established. Using fighter jets was similarly problematic. Not only is it expensive, but autocannon engagements at night carried a risk of plane loss from the debris. Nevertheless, through late 2022, a combination of SAMs and occasional air-to-air intercepts did shoot down many drones, preventing the collapse of civilian infrastructure already under pressure of regular missile strikes. But this was not sustainable or affordable long-term. By January 2023, Ukraine introduced a more nimble defense. Mobile air defense fire teams started patrolling likely approach paths. They used pickup trucks or light vehicles armed with heavy machine guns, or rarely, autocannons, paired with searchlights or thermal imagers. They linked into the National Air Defense Network via tablets, receiving current radar data of incoming objects. In some areas, acoustic sensors, basically arrays of microphones, were installed to detect the Shahed's lawnmower engine noise at long distances. And even ordinary citizens could report drone sounds through a smartphone app, which fed into the network. This decentralized, crowdsourced early warning, combined with many small, cheap gun teams, proved quite effective by the spring of 2023. Reports indicate that by early summer 2023, Ukrainians were shooting down up to 90% of drones launched on any given night. Russia quickly noticed that its new terror weapon was being blunted. To compensate, the scale of attacks started increasing, and improvements were introduced to the drones themselves. During the winter and into spring of 2023, Russia received more Shahed 136 shipments from Iran, but also stood up its own production lines due to technology transfer. The Russian-made models were dubbed Geran 2, and initially they were virtually identical to the Iranian ones. However, production was optimized for volume. Early Shaheds had wings and fuselage made of fiberglass laid by hand over honeycomb aluminum, too labor-intensive. By mid-2023, the Geran 2's fuselage top and bottom were being molded from carbon fiber in two large pieces, and the insides simply filled with foam for stiffness. The manufacturing of the copycat's MD-550 piston engine was also mastered domestically by September 2023. What's ironic is that those Iranian motors themselves were reverse-engineered from a German Limbach L550. These steps allowed Russia to ramp up output dramatically. By late 2023, Western intelligence estimated Russia's main drone plant in Alabuga was producing dozens of Gerans per day, potentially several thousand per month, and still scaling up fast. Indeed, Russian officials publicly set a target of tens of thousands of deep strike drones per year. Meanwhile, Ukraine's defenses also evolved. By summer of 2023, electronic warfare units were employing intense GPS jamming and spoofing against the attack UAVs. Since these drones cruise on autopilot via satellite navigation, strong jamming can cause them to go off course or even crash. Ukrainian forces set up electronic warfare barriers around key regions. and by mid-2023, this sharply reduced the accuracy of many incoming drones. Russia's counter to this was the introduction of a jam-resistant navigation antenna. The first upgraded models were seen in mid-2023, featuring 4-channel CRPA GNSS antennas, which can nullify interference from up to 3 jamming sources simultaneously. As Ukraine piled on more jammers, Russia responded around March of 2024 by switching to new 8-channel antennas, allegedly able to resist up to 7 jamming stations. By early 2025, debris analysis showed some drones with 12-channel antennas, and by spring of 2025, even 16-channel antennas, some of which were made not just in Russia, but also in China. Each step made the Gerans harder to spoof electronically, but also raised the cost and technical complexity. Starting around March of 2024, Russia also changed tactics by sending Gerans at a significantly higher altitude, roughly 2,000 to 2,500 meters, or 6,000 to 8,000 feet. Previously, Shaheds came in low, a few hundred meters up or even at treetop level, to avoid detection by radars. At 2.5 kilometers up, small arms fire is useless, and even many anti-aircraft guns can't reach. The only cost-effective NATO-supplied system Ukraine had that could reliably engage drones at that height was the German Gepard SPAAG with 35mm radar-guided cannons, but Ukraine had a very limited number of those. The result? Drone shoot-down rates dipped again. At the same time, Russia was churning out even more drones. A variant called Garpia A1 entered production, essentially the same Geran 2 design, but assembled at a different factory, the Ishevsk Kupol plant, and using a higher proportion of Chinese-made components. This not only boosted output, but also demonstrated the growing cooperation between Russia and China. Reports indicate that hundreds of Garpia drones were produced in late 2023, perhaps 500 in the second half of 2023, and a couple thousand in the first half of 2024, supplementing the main Alabuga plant's output, which by that point was in the tens of thousands annually. By late 2024, Russia was estimated to be able to produce 6,000 Shahed-type drones per month, a staggering rate that no Western country has matched in comparable cruise missiles or drones. As losses from Gerans mounted, first and foremost in the civilian population, Ukraine turned back to using combat aircraft, but in novel ways. On July 27, 2024, for the first time, a Russian drone was shot down by a helicopter, a Ukrainian Mi-8 with its door-mounted minigun. In the same way, even military transport planes, such as AN-26, were adapted for air defense. Ukraine was also quick to press some of its Mi-24 attack helicopters into night patrols to chase drones, and even Yak-52 trainer planes were modified. A second crewman with a machine gun would literally sit in the back seat of the Yak-52 with the canopy open, ready to fire at drones. These ad hoc methods sound almost absurd, but they illustrate the extent of creativity in countering the drone threat. And, while not sophisticated, the footage shows that it just works. Fighter jets, despite risks, were also back in the game, especially as the first batches of F-16s has arrived, boosting Air Force numbers. By early 2025, Russia began introducing a new Geran 3 drone. This was rumored to correspond to an Iranian design with a small turbojet or turbofan engine instead of a piston motor. The Geran 3 trades some range for speed, reaching 500 to 600 kilometers per hour, or over 300 miles per hour, versus 185 kilometers per hour for the prop-driven Geran 2. Once it first appeared in 2024, Ukrainian observers worried that their improvised interceptors might be too slow. Ukrainians managed to upgrade their designs fast, and by late 2025, there were instances of Ukrainian Sting drones successfully taking down Geran 3s in flight. Russia also experimented with giving the drones a defensive armament. There were reports that some Geran 2 and 3s were fitted with man-pads or older R-60 air-to-air missiles to be able to target Ukrainian aircraft trying to intercept them. This concept, a kamikaze drone that could shoot back at a pursuing fighter or helicopter, is still very experimental, and as of now, largely ineffective. The added weight and complexity likely reduced the drone's range and raised the price substantially. Another upgrade over time was the addition of cameras and upgraded communications on some Gerans. Originally, Shahed 136 and Geran 2 are pre-programmed one-way missiles with no live feed. Eventually, the Russians began adding SIM cards, connecting to 3G LTE networks, to some drones to transmit telemetry, and even then adding simple video cameras. Early implementations used off-the-shelf CCTV cameras and streamed low-quality video via cellular networks, basically for the operator to verify if the target was hit in the last moments. Later versions improved this with better cameras and thermal imagers. The data links shifted from relying on local cell networks, which could be jammed, to Chinese-made mesh network modems, allowing groups of drones to form ad hoc networks and relay data amongst themselves. This potentially enabled mid-course retargeting, with operator designating a new target if the primary one moved or was destroyed, and engaging moving targets, which a pre-programmed Shahed normally couldn't do. Some Russian deep strike drones were even spotted with Starlink terminals attached since 2023, enabling beyond line-of-sight control. SpaceX responded by imposing geofencing and mobility restrictions on Starlink use, and by 2026, only whitelisted terminals registered via the Ukrainian government are allowed in the country's territory. By 2025, Ukraine also started mass-producing cheap anti-air drones in the thousands per month, essentially making a parallel drone air force whose job is to hunt down Russian one-way attack drones. In fact, Ukraine formed a separate unmanned air defense command for the protection of the cities and civilian infrastructure. Its embrace of interceptor drones, costing just a few $1,000s each, is an acknowledgement of a new reality and should be quite a wake-up call for pretty much every military in the world, which is obviously not the case. The Russians, in turn, responded by adding rear-facing cameras on some Gerans, so an operator could see an interceptor coming up behind and potentially evade. There are also plans and prototypes for faster drones, Geran 4 and Geran 5, using more powerful jet engines to reach speeds of 500 to 600 kilometers per hour. They are also expected to be launchable from aircraft, giving them initial altitude and speed, and thus extending their range beyond what ground launches achieve. Meanwhile, warhead options on these deep strike drones evolved with time too. The original Shahed 136 carried about a 40 to 50 kilogram high explosive fragmentation warhead. By late 2023, Russia introduced a heavier 90 kilogram warhead variant, likely at the cost of some fuel and range. They also created different warhead types. Both sizes were made in thermobaric and incendiary versions. When used against civilian infrastructure, these variants can be especially devastating. The sad reality is that Geran 2 strikes have caused some of the worst civilian casualties and outages during the war, precisely because they are almost exclusively used in salvos of dozens targeting city infrastructure. At the same time, they hardly have a major or direct effect on the front line, as data shows almost all casualties are civilians, not army personnel. But as terror weapons and tools of economic attrition, they have been brutally effective. In some innovations that continue that fairly war crime-ish line, the Russians have experimented with equipping drones with landmines. A few Gerans were found to be carrying PT-M3 scatterable mines, apparently intending to drop them along roads or hit drone interceptors with them. Stepping back, the whole history of the Geran 2 use in Ukraine is a case study in how a precision weapon can be used primarily for strategic terror and attrition. The Russians built not just a drone, but an entire system and tactic around it. For example, to precipitate a humanitarian crisis in the colder-than-average winter of 2025 through 2026, they frequently use Geran 2's swarms to saturate Ukrainian air defenses around energy infrastructure, and then followed up immediately with ballistic missile and cruise missile volleys. The cumulative effect was hitting critical transformers, power stations, and heating plants, trying to knock out heat and light for millions in the cold. Similar attempts were also made every winter over the war, and while overall unsuccessful in completely destroying the power grid, they still did systematic harm. At some point, Russia also began accompanying waves of Geran 2s with decoy drones, Gerbera and Paradia. On September 9, 2025, Russia launched what appeared to be a massive drone attack not only on Ukraine, but into NATO airspace. Between 19 and 23 drones penetrated into Poland as far as 400 kilometers from Ukraine. These turned out to be unarmed Gerbera drones, essentially foam and plastic replicas of Geran 2 that fly the same speed and profile but cost a fraction of the price, perhaps 10,000 or less each. They carried no warhead, just a flight computer and equipment to imitate the radar signature of Geran 2s. The purpose was to trigger air raid alarms and force the Ukrainians, and in this case, Polish air defenses as well, to react. Indeed, Polish and NATO fighters were scrambled. A Dutch F-35 had to shoot down at least one using an expensive AIM-120 missile. We come back again to this pricing asymmetry because it is crucial. Russia is by now capable of producing around 6,000 of these drones per month at roughly $70,000 or less per unit. No country can produce the equivalent number of air defense missiles per month, let alone at a similar price tag. This is why interceptor drones, which Ukraine can build for less than $5,000 each, and in large numbers, are currently the only scalable and economically feasible counter. As usual, even after the Geran 2, along with Gerbera decoys, proved a success for Russia's campaign against civilian infrastructure, there were attempts on the Russian side to experiment with alternatives and complementary systems. One such category is smaller, so-called middle-strike drones, essentially mini Shaheds. One example is Delta, which is similar in shape to Geran, but with a smaller warhead and lower radar signature to slip through defenses. There are also UAVs like Cub-10, Izdalai-54 Italmis, BM-35, and a related BM-70, all of which carry 20 to 30 kilogram warheads. By early 2025, there was photo evidence of Italmis drones being used in Ukraine. With an estimated range of up to 200 kilometers, these fill a niche between the Lancet and Geran 2, and are more similar to the Iranian Shahed 131. It still remains unclear exactly what models and quantities Iran has provided to Russia beyond the Shahed 136. What is certain is that the Iranian drone deliveries, quite surprisingly if you haven't followed the war and not surprisingly if you have, far surpassed all drone deliveries from Ukraine's Western partners combined in sheer numbers. And another irony must be highlighted again. Both Iranian and Russian drones, though assembled indigenously, contain 90% components sourced from abroad or reverse-engineered for domestic production. Yet Western countries at this moment cannot compete with Iran, Russia, and now China, which is catching up fast through partnership with the other two, in the quantity and even the quality of combat drones. The reasons behind this are complex, but one explanation is that Russia has the crucial advantage of being able to test any new weapon immediately in a high-intensity war, as does Ukraine with its own innovations. This means designs that don't work get weeded out quickly after first combat trials, while designs that prove effective are rapidly refined. It ensures a high degree of efficiency. Resources and labor are poured only into things that show results on the battlefield. Both Russia and Ukraine, by Western standards, have fairly modest defense budgets and limited high-tech industrial bases. Yet both have innovated at breakneck speed under fire. Russia's cooperation with Iran and China also plays a fundamental role. By combining Russian and Iranian wartime experience and innovations with China's vast manufacturing capacity and electronics, they have all benefited. Unlike in some alliances, there are essentially no internal divisions between them, and their focus remains on getting as many moderately priced and battle-tested drones as possible into the next big fight. Having stepped quite far into the strategic and geopolitical weeds, let's circle back to cover one last category of drones. The kind of system where Western countries, particularly the United States, still have an advantage. Probably the most famous such UAVs in the world are the American MQ-9 Reaper and Turkish Bayraktar TB2. These are big, expensive drones that can fly for 24 to 48 hours at altitudes of up to 9 kilometers, carrying sophisticated sensors and precision weapons. At the start of the Russo-Ukrainian War, TB2s were heralded for impressive battlefield performance. However, as the conflict intensified, all large drones became highly vulnerable to modern air defenses. Since then, Ukraine's use of those has been extremely limited. So, the era of male drone dominance is arguably coming to an end on high-intensity battlefields. Their advantages, long endurance and dual ISR strike capability, are outweighed by their disadvantages, cost, size, and vulnerability. A Bayraktar TB2 costs several $1 million. An MQ-9 Reaper about 20 to 30 million, and only a few hundred of those were built. Losing even one is a strategic and political event, whereas Russia losing a small Orlan or Lancet is just a daily routine. Finally, a high-flying Reaper or TB2 is also a fat radar target for any halfway decent SAM system. Indeed, one reason Russia had issues deploying its own male drones extensively is precisely this. but they still exist. For example, Orion, developed long before 2022, is roughly in the same class of a smaller Reaper, can carry up to 4 missiles or glide bombs, but usually seen with 2, as well as lacking a crucial satellite communication module present in most analogs. A few dozen were built. It was reportedly used in Syria, and there have been a handful of videos of it being used in Ukraine, launching Kornet or Vikir anti-tank guided missiles at targets. Its impact has been negligible, partly because Russia never had many, likely under 50 in total, of which at least 10 have been lost, and partly because its sensors are quite weak. Many Orion strike videos show a very blurry thermal image where it's hard to even discern the target. The Orion's primary armament is the Vikir-1 laser-guided missile, while it also can drop small guided bombs. When these weapons hit, they certainly can destroy armored vehicles, but getting in range and guiding them without being shot down is the trick. The further development of Orion led to a twin-engine variant called Sirius and a larger, high-altitude, long-endurance drone called Helios. These have appeared in shows and tests, but only a handful of prototypes exist. Since the all-out war began, Russia has de-emphasized male drones in favor of smaller, cheaper systems that can be lost in large numbers without breaking the bank. In fact, Russia's other male projects, like the Altius, another heavy twin-engine drone, and Korsar, a smaller tactical male UAV, has been slow-rolled or even paused. Interestingly, the most actively used Russian male drone in this war has been the Forpost, which is actually a licensed Israeli design. Russia had an agreement before relations soured and built some 30 to 100 Forpost drones. Initially unarmed, around 2021 they unveiled an armed variant capable of carrying small bombs such as the 20-kilogram CAB-20s. A few videos in 2022 showed Forpost drones dropping munitions on Ukrainian vehicles, with some success. But again, the scale was small, and at least 6 were confirmed shot down. At the same time, work was conducted to modify this male UAV to increase the number of bombs from 2 to 4. Iran also contributed here. They supplied some Mohajer 6 drones to Russia in 2022. The Mohajer 6 is roughly analogous to a TB2 and can carry 2 to 4 small guided missiles. Russia used a couple in the fall of 2022. One was famously captured almost intact after it glided into the Black Sea, revealing once again an assortment of Western electronics inside. Like other males, the Mohajers were easy prey for SAMs upon approach for attack, so they haven't featured prominently since. Finally, we come to a sort of apex system, the S-70 Okhotnik B stealth UAV. This is a large, jet-powered flying wing drone Russia has been developing as a loyal wingman for its Su-57 stealth fighter. It's supposed to have a reduced radar cross-section, internal weapon bays for up to 2,000 kilograms of guided bombs, and the ability to coordinate with a manned fighter. Russian media hyped it up as a revolution in drone warfare, forgetting to note that it is actually the Russian copy of the Iranian copy of the American RQ-170 Sentinel that was reverse engineered after crashing in Iran in 2011. Back then, the loss of an aircraft was attributed to the loss of command and control connectivity to it. Ironically, the Russian Okhotnik, 13 years later, will be lost due to the exact same reason. On October 5, 2024, the drone was accompanying an Su-57 over eastern Ukraine. According to multiple sources and video evidence, the drone malfunctioned due to a loss of communication and started to stray. To prevent it from possibly falling into Ukrainian-controlled territory, the Russian operators made a drastic decision. The Su-57 shot down its own wingman with an air-to-air missile. The S-70 crashed near Konstantinivka, which was behind Ukrainian lines, and wreckage was recovered together with, once again, Western components inside, and a UMPBD-30SN glide bomb. This was one of 4 prototypes built in 13 years. In summary, Russia's male and hail drone programs have had minimal effect on the war. A few were used, some were lost, but in practice, Russia found that a combination of many cheap drones was more effective than a few expensive ones. This mirrors Ukraine's experience and, to an extent, even Western forces' observations from Ukraine. A $30 million Reaper is a fantastic asset in an uncontested environment, but in a peer conflict with dense air defenses, its survivability is questionable, and its cost-effectiveness is terrible compared to swarms of 30K loitering munitions. To illustrate, for the price of one MQ-9 Reaper, you could equip an entire unmanned systems battalion of small drones. In fact, for the cost of one Reaper, roughly 165 Orlan 10 drones could be procured, using the 200,000 unit cost from pre-war contracts. And 165 Orlans covering the front will likely gather more intel and be harder to fully suppress than a single sophisticated American UAV. Similarly, instead of one Reaper carrying 4 Hellfire missiles, you could launch dozens of Lancets and hit dozens of targets. Yes, the Reaper's Hellfires are more reliable, and it can return to base to rearm, but in the meantime, you'd have to keep it safe from SAMs as well as meticulously trained crews to operate it. The extensive use of UAVs by Russia in Ukraine, from tiny quadcopters to long-range variants, has serious implications for Western militaries. This war has provided a glimpse not just into the present, but also into the future of warfare, where drones are ubiquitous and can fundamentally challenge traditional concepts of both defense and offense. UAVs are no longer individual tech toys, but parts of wider doctrines and interlinked systems around which entire military units are built. Western analysts and think tanks have increasingly sounded the alarm, noting that Russia, while losing a lot, has also developed an overlapping series of asymmetric advantages in this conflict. And we hope we have highlighted this clearly today. The first key takeaway is that Russia, with direct help from Iran and China, has developed mass production of relatively simple, cheap drones in almost every category, from large and small ISR UAVs to heavy strategic deep strike systems. They have established a supply chain that efficiently bypasses sanctions and an industrial base capable of churning out tens of thousands of various UAVs monthly. Western defense establishments, by contrast, are used to buying a few dozen exquisite drones over many years. Even attempts to scale up production of basic ISR drones often end with contracts for hundreds, or at best a few thousand units spread out over long timeframes. Regardless of the drone type, this is the equivalent of signing a procurement contract for a few hundred cartridges for a modern army. Western forces, which field far fewer drones per unit, risk being outnumbered and out-informed on future battlefields if they do not catch up in scale. The second key takeaway is that Russians formulated a very specific approach to how a wide variety of drones are used together. Cheap decoys are employed to saturate radar screens in airspace so that more expensive weapons can slip through. Any strike drone is ideally paired with an ISR drone to verify the target, guide the strike, and observe the outcome. Different drones fill clearly defined niches, are highly specialized, yet retain the ability to work together as a single system that amplifies overall battlefield effect. Reconnaissance must be deep, continuous, and resilient, and the loss of any individual drone should never break the flow of information. Finally, every unit must be a drone unit in some form. Just as almost every battalion today has mortar, reconnaissance, or heavy weapons elements, it should also have an organic drone component to fully remain combat capable. At the same time, more complex tasks, long-range strikes, layered ISR, electronic warfare integration, and interceptor operations must be concentrated in dedicated drone-only units, focused exclusively on this domain. Almost all these principles Russia now follows closely, though it did not invent them, but largely copied them from Ukraine. Yet while Ukraine has effectively shared these hard-won lessons with the West in real time, complacency was chosen over imitation or innovation. The third key takeaway is the increasing role of the radio environment. And this is the part Western militaries still tend to treat as supporting infrastructure rather than as a primary battlefield. We already told a fascinating story of adaptation and countermeasures around Geran 2 drones. But if you strip away the paint, engines, and even the warheads, the real war was happening in the invisible layer. Navigation signals, data links, jamming, and control. Ukrainian spoofing and electronic warfare did not merely reduce accuracy. It forced Russia into an iterative cycle of hardening. Better GNSS antennas, more channels, new receivers, altered flight profiles, improved communications, and eventually even attempts at mid-course retargeting and airborne relay networks. In a drone war, air defense is not only missiles and guns. It is spectrum management, electronic attack, signal discipline, redundancy, and the ability to operate when GPS is unreliable, cellular networks are degraded, or the radio spectrum is actively contested. The side that can still see and talk under those conditions, or deny those abilities to the enemy at scale, does not just gain a tactical edge. It keeps its entire drone system alive while the opponent collapses, first in the electromagnetic domain, and then on the ground.